Okay, how you doing? My name is John Hurley. I'm a software engineer at Metronome, and really this is going to be a run-through of the project that the team I'm involved in have been working on over the last period of time. Basically to do with connection tracking within OVS and to try and improve the performance we're getting here. So, quick run-through of what I'll cover. I'll give a brief background to Conntrack within OVS. Obviously mentioned OVN here, but I think a lot of this has already been covered today, so I'll not dwell on it too long. Nick already has given an overview of some of the offloading we do, and I'm sure you won't be surprised when you hear that I work for Metronome that I'm going to mention offloading. So I'll probably jump in straight into that and kind of give a high-level overview of how we offload Conntrack to our SmartNICs. I'll give some performance figures from this and show sort of the results we're achieving. And from this, I'll move on to more our kind of a research on our experimental things we're looking at and how we're trying to improve performance, both for our offloaded situation and maybe things that can be applied to OVS and to improve performance there. So we'll start off with a diagram of really OVN, or a part of OVN that mainly security groups that we're interested in here. Blatantly stole this diagram, but I've referenced a lot of people who are probably sitting here. So I like the diagram. It just gives a simple overview of the changes from before OVS 2.5 and OVN, before it started handling this, and before security groups really moved to the switch. So in, say, an OpenStack setup, as we have on the left here on, say, pre-OVS 2.5, if we wanted to do security groups, we were probably going to plug in Linux bridges between the switch itself and the VMs, then use iptables here. So from 2.5, this moved and everything was pushed down, so we can actually handle this on the bridge and support the rules on the bridge, and of course do this, as has been brought up quite a bit today, using connection tracking and the Linux connection tracking modules. So on the left is a bit of a messy depiction of how OVS would currently work from traffic coming in from a network and going out to the network, but going through connection tracking. I've kind of tried to highlight with the black line the first packet, and with the red line the second packet or the third packet, and really the fast path packets here. So the idea is that the first packet comes in, it goes to the Linux kernel module or the OVS kernel module. It tries to do a match. Chances are it won't match if the rule hasn't been passed down yet, so it will go to user space. User space will decide that this requires a contract action. It will inject back to the kernel where Conntrack is applied here. This will be sent then to the netfilter contract module. It will do its 5-tuple lookup, basically determine the state of the packet within its flow, whether it's creating a new connection, part of an established connection related to another connection, and we'll apply this metadata to the packet. The packet can then recirculate back into OVS where it can be matched with this state information. Again, for the first packet, there's a fair chance that this won't be matched, and again, we'll go to user space, and we'll come back down, implement the action, and the packet will go out on the network. For the second packet comes in, hopefully these rules have now passed down to the OVS kernel module, and from the red line, we'll be able to match in the kernel module, go to Conntrack, recirculate here, and execute our actions, hopefully out on the network. So on the right, as Nick said earlier, what we do is really offload this Linux OVS data path and offload the rules there. So this is how we've added Conntrack into this. So the basic point to take here is that all connection tracking lookups and all of this state tracking takes place on the SmartNIC. None of it now takes place in the kernel. This is really, the idea of this is to keep the synchronization right. I mean, it's obviously easier rather than trying to synchronize, say, kernel tables and tables on the SmartNIC, but it's also more secure. If we have it all in one place, we're not going to misclassify things, which is a potential security breach. So again, the first packet will come in. Chances are it will miss any of the rules that we've offloaded to our SmartNIC, go through the kernel, go to user space. This time, instead of going to the Linux connection tracker, we'll grab the packet here. we'll extract the 5 tuple and we'll send a request down to our SmartNIC. So we'll do the lookup basically here, and we'll send a response back to our module here. From here, we can populate the metadata, the packet metadata, in the same way that Conntrack or NetFilter Conntrack would have, and we'll pass it back into OVS kernel, and it will not know any different and can continue to execute the packet. It means now that our second packet can come in. Hopefully the rules again will have passed down. We can match it on the SmartNIC, and we can also do Conntrack on the SmartNIC and just pass out of the system. So these are some results we get here. So this is a test with, I think, 10,000 unique TCP flows. The red lines represent a pure OVS test. The blue lines are with this offloaded connection tracking. There's 3 tests shown here. The first one is we've just called cut through, which is kind of our benchmark, match a port and send to another port. So there's no Conntrack taking place here. The second one we have match, send to Conntrack, recirculate, and do a match on the Conntrack information and output. And we've also added a third one, which is a double recirculation. So we're sending to Conntrack twice, possibly, well, 2 different zones. Again, this is something when playing about with OVN we saw, where you may be sending from one VM to another in the same system, and it may actually go through 2 different zones for each VM. So it'll actually go through connection tracking twice and recirculate twice before getting through. So I'll not dwell too much on the results, but hopefully you can see that we are improving the performance when compared to standard OVS. And in this test particularly, we're freeing up a lot of CPU usage. The OVS tests we carried out were quite CPU intensive. I've highlighted in green here, but from probably an engineering and a software engineering perspective, something that doesn't sit too well with us. So we have the dark blue line is our simple cut-through test, and basically there's a massive drop in throughput when we go to do this connection tracking. So having to pass our packet through the pipeline on the SmartNIC and holding on to the packet that long, doing the recirculation, it hurts us. I mean, we can still get okay performance, but it does hurt us. And probably if you look at some of the larger packet size tests on standard OVS, you can see a similar thing happens. Taking the time to send to the Conntrack module within the Linux kernel and recirculate, it can have an effect here. So we want to look at ways which we can try and improve this, and this is one thing. Proposal we've put forward is this: we're calling quite unimaginatively assume established. It's actually quite similar to the approach that Ben was talking about in his talk earlier, where we're really trying to cache what is going on here and avoid a lot of the inner steps if we can. So a couple of assumptions, or maybe more so observations, that led us to this. The first thing is that the majority of packets are going to be in the established state. You know, assuming the network isn't under attack or anything, assume most people are happy to accept that. Packets will tend not to be forming new connections. It will be part of an established connection and doing something useful. The second observation we made when looking at quite a few rules was that basically the packet key before and after we do the recirculation is essentially the same. The only difference really is the Conntrack metadata. But that metadata doesn't really exist outside of the pipeline. So can we, as the diagram suggests here, try to cache this information and basically match on our packet key? And if we get to, say, an established state, do we really need to go around this recirculation process? Can we forget about all this inner metadata that exists and just sort of bypass straight through, cut straight through? So what we really do is we assume that the packet is established. If it is, well then we just get the action and go and do it. If it's not, we do full processing. So we still have the ability to pass the packet to the connection tracker and to recirculate it and do it as a slower path, as it were. So when doing this, obviously we want to be very careful that there's no security breaches and we still are keeping correct state. So I'll try and explain with a diagram. Hopefully this shows a bit better. I've just given a simple example of 3 rules here. First rule matches on minus tracked state, so no connection tracking, say a UDP packet, and as an action we send to Conntrack to a particular zone and we recirculate it. Then when the recirculated packet, we will hit probably one of the other two rules, which is either a new state or an established state, and we'll just output to a port. So we have this flow cache existing on our current architecture, so we utilize that. The black lines here show at the minute how a packet could go through. So the first packet will come in, or the packet will come in. It will match this minus track state. It will go to, we've called it the multi-hash here, really the data path rules coming down from OVS. We can get our action, which is obviously send to Conntrack and recirculate. We'll send to a Conntrack processor, and then we can recirculate around where we may add new entries to the flow cache. But with this proposal, the Conntrack processor tries to determine if a packet is now moved to an established state, and we can also indicate with flags and rules whether it's legitimate to do this. There are situations where we can't do it. For example, in a double recirculation, where if we try to do this, we could have basically infinite loops. So we do try and be careful with that, but the idea is that the Conntrack processors here will determine that we've moved to an established state, and we'll try and add this new entry into the flow cache on the recirculation. So this new entry basically has an established state, and all of the other Conntrack metadata set to 0. More importantly, probably the recirculation ID. So the idea being that we can never really have a situation other than this, where the recirculation ID is 0 and the state is established. If a packet has state, it kind of has to have been recirculated, so it can't have a recirculation ID of 0. And then basically any packet that comes into the system, we force its metadata to established plus established and a recirculation ID of 0, and we do look up in this flow cache. If it isn't in the flow cache, then we just reset its data to minus track, and we let it take the slow path around. If it is established and it's part of a well-formed flow that's already stored in the flow cache, well then we don't need to do all this inner processing, messing about with metadata, recirculation. We just take the action that we've already got from our OVS rules and we implement it. So some initial results on this. The top graph probably shows ideal results for us with 10,000 unique TCP flows, all of which are established. So you can see I've highlighted in green again the improvement. Now we've basically got our recirculation throughputs up to the same as our simple cut-through results. The actual cut-through test here has dropped because we are doing a double lookup in some cases when new packets aren't, or when we're not matching in this established state in the flow cache. The lower graph is probably more realistic. We've moved to 20,000 unique TCP flows, 10,000 established, 10,000 are unidirectional. So in theory in this test, 1 in every 3 packets will hit the new state. But if we compare the red, which is our simple offloaded OVS with our Conntrack with the blue, which is with this technique applied, you can still see that we are greatly improving throughput when pushed over this. So pretty much finished. Just give an idea of some of the future work and hopefully answer some of the questions before they come to me here. One thing people are probably going to say is, if we do this sort of caching, where is the state tracking going? That's not something we've added. These are experimental results at the minute, but it's on the list. So the idea would be when our Conntrack processor tells the flow cache that we can add this kind of fast path entry, that we also give it a pointer to basically the Conntrack state information within the Conntrack table. So we can, luckily when we are in an established state, the TCP state tracking stuff is quite simple. Really just check window sizes and acknowledgement numbers, compare them with windows and things. So we hope to be able to just do a simple check, and when we do match in the flow cache, do a simple check that this packet is valid and move on. So again, we'll have some further optimizations to make here. Some things we're working on that, we showed that the cut-through test was slightly down in this, so hopefully we can add a few simple things that will bring that back up. Some corner case handling, yes, we've got to deal with. Of course, the beauty about this approach is that if something can't, some pipeline can't function with it, then we just let the packet go to slow path. We get the same throughput as we reported earlier anyway. And then maybe more general things with Conntrack that we're looking at. There's a bit of a discussion on the hardware offload about synchronization with kernel and with SmartNIC offloaded stuff. It was mentioned with maps and eBPF, for example. Obviously here we're doing all this connection tracking on the SmartNIC. So at the minute, there's a separation between what's going on our SmartNIC and what's going on in the Linux kernel. Do we need, it's probably a whole different presentation, but do we need to do more synchronization here and get stuff balanced between them? Or are we okay to say that anything that's gone through OVS and connection tracking will have its own zone, so it's kind of going to be separate from anything that might be utilizing the connection tracking tables in the kernel? So are we okay just to entirely separate it? And then finally, one thing we're kind of excited to get on to is the introduction of NAT in OVS 2.6 and its close connection with Conntrack. So obviously in the first kind of diagram we showed of the Conntrack offload, we want to get it in there, but we also think that NAT might be something that fits into this kind of flow cache setup as well. We may be able to fast path it. So, yep, that's pretty much all I've got to say. If there's any questions.
We have time for some questions, so.
You mentioned that the techniques that you've been experimenting with to accelerate would also be possibly applicable in software implementation in kernel or in user space data path. Have you thought about upstreaming that?
No, not as yet. It's kind of experimental, and we have been really working off what we have, which is the offloaded stuff. But yeah, is there any reason we can't kind of cache a full flow in the OVS kernel and have connection tracking bypass, so we don't need to send to the Linux connection tracker? Again, it's not something we've done, but it's possibly something that could be looked at.
Do you have any patents on that would prevent this?
You're talking to the wrong person.
Hi, Jim. I'm really excited about this because I'm playing with Conntrack these days and seeing that beautiful number. It's great. And my question is, can I play with this? To play with this, what do I need to get that?
Well, you need to talk to Metronome salespeople and buy some products. This is basically stuff we've been doing on the SmartNIC. So again, it's fairly experimental. There isn't, as the last question, there isn't an OVS data path implementation of this at the minute. So no, unfortunately, there's nothing. Sorry, can you repeat?
So if you have like a physical bridge and then the integration bridge, and then typically the logical switching is done at the integration bridge level.
Sorry, I'm not.
Because
you may have to explain it.
That the contract actions are associated with the integration bridge, which is virtual. The device is virtual; it's not a physical device.
Yeah.
So how do you synchronize state between the virtual interface and?
Yeah, well, I think I showed that in the diagram. Basically, instead of sending to the Linux connection tracker, we kind of grab the packet and we send a request down to the SmartNIC. And we do basically a simple lookup there, or well, not a simple lookup. We do a lookup and we do our connection tracking, our state tracking. We send a result back. This works with OVS at the minute. It could be added into, say, iptables or whatever else once we use Conntrack with. But at the minute, it's hooked into OVS.
Let's thank our speaker one more time.